Hello everyone, Chicken Puck here. It's hot, bro. I'm sweating so bad in here. Today we're going to be looking at Superdense coding, which is one of the clearest examples of how entanglement can be used for quantum communication. If Alice and Bob share an entangled pair beforehand, Alice can communicate two classical bits while physically transmitting only one qubit. So how is this possible? It comes down to the codebook. Alice and Bob are initially going to share the phi plus state. But what's happening here is we have Alice sharing the first qubit and Bob sharing the second qubit. Alice would have this ket 0, Alice would have this ket 1, Bob would have this ket 0, and then Bob would have this ket 1. Now suppose Alice wants to send Bob one of these messages. There's an important distinction here though. The classical message 00. Also, I'm going to put the 4 bell states on the screen here so you can kind of see what's happening. If Alice wants to send 00, 01, 10, R11, Alice and Bob are going to agree on this encoding beforehand. This 00 is not the same thing as the 00 in the bell state. These are classical bits Alice wants to send. If Alice wants to send 00, she applies I to her qubit. For 01, she applies Z to her qubit. For 10, she applies X to her qubit. For 11, she applies ZX to her qubit. Each operation transforms their entangled pair into a particular bell state. So the entire bell state acts as an encoding on Alice's message. So if Alice wants to send 10, she would apply X to her qubit, and that would transform phi plus into psi plus. So then Alice sends her one qubit to Bob. Bob already has the other half of that entangled pair, so now he possesses both qubits. Then he'll perform a bell state measurement, and then he sees the psi plus, and then he looks at their codebook and sees that that means 10. So that's the idea of how superdense coding works. But why does this codebook actually work? Let's prove it. So first thing we need to do is prove that these are valid quantum gates. So we need to prove that they are reversible. So we have to prove they are unitary. So let's do that first. To prove unitarity, we just need to say that U dagger equals I. We know that I equals I, and then we know that Z, poly Z squared equals I, and poly X squared also equals I. So what we can say here now is X and Z are unitary. So we've proven the first 3. Now we need to prove that ZX dagger also is identity. So taking ZX to the dagger, we're going to reverse the order by the adjoint property. And so we're going to do ZX. We're going to bring in the dagger, and we're going to get X dagger Z dagger. But since X and Z are unitary, we can write this as ZX X Z. And then therefore, we can just say this XX would be I. We would get ZIZ, which would just be I. So therefore, the ZX is also unitary. So now we also want to prove that Alice's operation is unitary as well. So we have UA, which is her operation here, tensor to IB, which is leaving Bob's qubit alone. So we want to prove that Alice's operation is unitary. By property of tensor products, we're going to get UA dagger here, tensor to IB, since the I transpose is itself. So we're going to get IB. And then since this is unitary, this is going to be equals to IA, and then tensor to IB. So this is a valid operation on the 2-qubit system. Now let's see how they change the bell state. So let's say Alice wants to send the 10, so she'd apply an X to her qubit. We're going to get X on Alice's first qubit, which would make this to a ket 1. We're going to leave Bob's alone, so we're going to get ket 0. Then we're going to do X on Alice's qubit here, which is 1. Then we're going to get a 0. Bob's will be left alone. We're going to put that under square root 2. But if you notice, this is exactly psi plus. So following the code book, we have 10. We apply the X, and then we get out the psi plus. Now let's do ZX. So the X would go first, and then the Z. So then X acting on 0 would give 1. Z acting on the 1 will apply a phase of -1. We're going to get negative ket 1 for Alice's qubit here. B will be left alone, so we're going to get 0. Then we're going to plus with X goes onto Alice's qubit here. We get a 0, and then applying the Z does nothing. So we're going to get 0 here. Bob will be left alone, so we have 1 all over square root 2. And rearranging, you will get that this is equal to psi minus. So going back to the code book, we have Alice wants to send us 1, 1, so we apply that ZX. And then we get out psi minus. So now we can see what the math is actually doing here. So using only her operations on one half of the entangled Bell pair, she maps those 4 messages onto 4 distinguishable Bell states. She then physically sends her qubit to Bob. So then Bob now has both qubits. So he will then perform a Bell measurement and then uses that agreed codebook to see what the message was. And then the 4 possible messages contain log 2 of 4, which is 2 classical bits. So provided Alice and Bob already share entanglement, 1 transmitted qubit goes to 2 classical bits. And that's superdense coding. So in case that didn't make any sense to you and you want the plain level English, here is what's happening. Alice and Bob share this state. Alice has qubit A and Bob has qubit B. Alice will encode her message. So if she wants to send 1, 0, she will apply X to her qubit. Then the joint state will be psi plus. Then Alice will send her qubit to Bob through a quantum channel. Keep in mind only 1 qubit is transmitted. So Bob already had qubit B, but now he has both qubits. Then Bob performs a Bell measurement. So in the Bell basis, he will get out psi plus. Then Bob will decode the message. Since psi plus means 1, 0, he knows that Alice meant to send 1, 0. Thank you for watching.